All right, so let's look at this one. We've got this link AB that is rotating with a clockwise angular velocity of 10 radians per second, and we want to find the velocity of the piston C right here. So, bar BC, do you see that bar? Yeah, sorry here. Do you see here that bar BC is the main bar, the bar it's not in pure rotation, and so we have to use a method to find the angular velocity of that bar, or in this case the velocity of point C. So we are in the instantaneous center of zero velocity section. So let's use that method. Let's use the instantaneous center of zero velocity for bar BC to find what we're kind of looking to find. All right, so step one, draw the velocity vectors. Do you see that the velocity of C is going to go straight up? So I would draw my dotted radial line perpendicular to that. And the velocity of point B is perpendicular to the link. So the link is a radial line. The link would be the line that I'm going to extend. All right, and so my instantaneous center will be somewhere right out there. Okay, so now I need to find this distance RC and this distance RB. So I kind of look and ask, okay, what do I know about some angle? Do I know some angles? Do I know some distances? And so I'm going to draw this blue triangle right here and kind of ask myself, do I know some things about that blue triangle? All right, well, I know one side is 0.75 and the other side is RB, the other side is RC. It's not a right triangle. So I can't just use sine of something or cosine of something because it's not a right triangle. I know one side. Do I know any angles? Yeah. I don't know if there's a great way that works every time, but a few things that I do is I look for not complementary angles, right? I look for 90-degree angles, and if I know part of it, so look at this. If I know this angle right here is 13.6, then shouldn't that angle be, add up to 90 degrees? And so this one is 76.4. Okay, and now I know if I can just get one more of those angles, then I know that the three angles inside of a triangle should add up to 180 degrees. And so then another thing I like to do is, even though I'm looking at that blue triangle, sometimes it's helpful to look at some other triangles. One option might be this triangle right here. Might be helpful to look at that triangle right here. If I know that's 13.6 and I know that's 45, then I can find that angle, so I could maybe find that other angle. It adds up to 180. So looking for other triangles, looking for angles that add up to 90 or angles that add up to 180. Do you see this triangle though? Also, I think this is the way I'm going to go. Is by looking at a very, very large, very, very large outside triangle. That is a 90-degree right triangle. This angle down here is 45, and so that angle up there has to add up to 180 or add up to 90. So this angle up here is going to be 45 degrees. All right, and so if I know that one angle is 76.4, one angle is 45, that other angle has to add up to 180. That angle, 58.6 degrees. All right, and once you know one side and all of the angles, it's almost like, I'm having flashbacks to 9th or 10th grade, angle, side angle, those proofs, or, we can find the rest of it. We can't just use the right triangle, but we can use the law of sines. Do you remember the law of sines? Maybe not. law of sines would say something like sine of alpha over the distance A equals sine of beta over the distance B equals sine of the other angle, I'll call it gamma, over the distance C. These angles are just opposite each other. So sine of alpha over the side opposite alpha. Sine of beta over the side that's opposite, looking at that angle. Sine of gamma over the side opposite. Okay, so what do I know? Let me look at this 0.75. I know that the sine of 45 over 0.75 would equal, let's see, how about the sine of 58.6 over RC? Right? So there we go. I can I can find RC would be 0.9056 feet, but I could kind of keep going. The sine of, let's see, the other one's 76.4 over RB. So still say, okay, that's equal to each other as well. So I would get RB 1.031 feet. Now, double check that your sides make sense. The larger the angle, then the larger the length opposite it. Same thing with sines. I mean, the larger the angle, the larger the sine. And so, yeah, it makes sense that RB is 1.031, RC is 0.9056, and the smallest angle would have the smallest side opposite, 0.75. All right, that's the hardest part of the problem. Now, V equals R omega, V equals R omega, V equals R omega. Where should we start? Where should we start? Well, we're given this right here. We know this length right here. I'm going to start down here at link AB. And I'm going to write this out to myself to remind myself, okay, what am I looking at? I'm looking at link AB. And I know V equals R omega. So I would say velocity of point B would equal R of that link AB times omega of that AB. And so this is a length of 0.25 feet and then an omega of 10 radians per second. All right, so 2.5 feet per second would be the velocity of point B. Now, I'm staying with that point, but now instead of looking at this link AB right here, I'm looking at my bar BC, which is really, I'm pretending it is glued on top of this imaginary disc whose instantaneous center is right there at the top left right there. See? All right. So, let me remind myself, I'm looking at link BC, which is really the imaginary disc. Right? I'm looking at the instantaneous center. And the only equation I'm going to use, V equals R omega. So this VB, all right, so now this R would not just be 0.75. It would not just be RBC. That's got to be the R to the center of rotation. So this is the RB right here, the 1.03 feet that we found. Times omega. Also, it's not the same omega. I'm not looking at the same rigid body. Now I'm looking at BC. So I know this 0.25 equals 1.031 times omega BC. Omega BC would be 2.43 radians per second. I've got to visualize that myself, but if we started going clockwise here, then that means the velocity of B would be in this direction. If the velocity of B is in that direction, that makes this counterclockwise. So this would be 2.43 counterclockwise. Okay, now I'm going to stick on the imaginary disk, but now let me look at VC equals RC omega BC. And so I can still use that 2.43 and say VC is equal to RC 0.9056, 2.43, 2.2 feet per second. I've got to visualize it again because this actually could be up or down, but if my imaginary disk is rotating counterclockwise, then C is pointed up right there. So this is up right there, velocity of C. I think that's what it asked for. Determine the velocity of the piston C. So this is very helpful. We're only looking at this snapshot, but it is very helpful to determine the velocity of a piston if you know the angular velocity of this rotating link right here that is making the piston go up and down. Let's take a step back. Let's take a step back and look at this. We knew that bar BC was the main bar. That was the bar that we wanted to find the instantaneous center. So I found the instantaneous center right here. And then what equation did I use? I used VB equals RAB omega AB. I used VB RB, V equals R omega. The only equation I used was V equals R omega. Let's rewrite each of these. I started with VB equals R omega. And then I took that, I took that VB and looked at a different rigid body. Then I stayed on that rigid body and looked at a different point. And so I snaked my way through this problem to get to VC. So there's a good visual about how we're going about solving these types of instantaneous center problems. All right.